continue talking about volatile substances and colligative properties. So last chapter we talked about what a volatile solution is and what vapor pressure is. So we're going to talk in this section about what happens when two volatile compounds or solutions or liquids are mixed together. So recall, a volatile solution just means one that evaporates and has some kind of vapor pressure, which is the pressure exerted by the gas above the liquid. And the more volatile the substance is, then the more vapor pressure that it has. So the total vapor pressure of what is called an ideal solution, so a solution again being a mixture of two components, and in this case we're talking about two volatile liquids, it depends on the vapor pressures of each of those two components in the solution. So for example, if we had a mixture of water and ethanol, the total vapor pressure would be a combination of whatever vapor pressure is from water and whatever vapor pressure is from the ethanol. And the vapor pressure is determined both on the vapor pressure of the pure substance as well as how much of that pure substance is within the solution. So for example, if there's a 50-50 mixture of ethanol and water, it will have an overall different vapor pressure than if we had a 20-80 mixture of ethanol and water. So we want to know about how many moles of each of those components are in the mixture, and for that we are going to discuss what a mole fraction is, and we'll get into that a little bit later in the next few slides. So we'll talk about what a non-ideal solution is later, but when we want to talk about an ideal solution, that is one where the intermolecular forces between all the molecules in the solution are comparable. So when the intermolecular forces are a little bit different, that's when a predicted vapor pressure that we would get from this calculation down here would be a little bit different than the actual vapor pressure that we see. And we'll get into that a little bit later. So for a mixture containing more than one volatile component, for example, again, water and ethanol, the total vapor pressure is going to be a combination of the mole fraction of component 1 multiplied by the vapor pressure of the pure component 1, and we're going to add to that the mole fraction of component 2 times the vapor pressure of pure component 2, and so on and so forth. This is called Raoult's law. Okay, so the mole fraction given by this guy here, that's called chi. Okay, and the little 1s and 2s and 3s in that expression are just referring to which volatile component we're talking about. So for example, maybe this particular part of the equation talks about water, and then maybe this particular part of the equation talks about ethanol. So we're going to talk about a couple different ways to express concentration. Now, molarity is one that you've already been exposed to and you should be very familiar with because it's one of the most common ways to express concentration, and that is just the moles of the solute divided by the volume of the solution, so moles per liter. Now, mole fraction is a ratio of the moles of solute to the total moles of the solution. So for example, in our ethanol water example, if we assume that ethanol is the solute, then we want to have the moles of the solute, so the moles of ethanol on top of the fraction, and on the bottom of the fraction we'd have again the moles of the ethanol or the solute, and we'd add to that the moles of the solvent. So the bottom of the fraction is the total moles of all the components of the solution, and that is the mole fraction of the component that is basically on the top of that fraction. So if we wanted to figure out the moles fraction of ethanol, right, so this would be ethanol up here, and then this would be ethanol here, right, and then this might be water, right, solvent, water, solute, ethanol. So to do this calculation, this would figure out what the mole fraction of ethanol is in a solution of ethanol and water. Now we can use something called fractional distillation to separate these particular mixtures. So as we're talking about ethanol water solution, the difference between ethanol and water is that they have different vapor pressures, which means they have different boiling points. So if we have a mixture of ethanol and water, what we can do is we can use this method called fractional distillation to selectively separate the ethanol from the water. And basically the way it works is that as the solution is being heated up, so it's being heated up down here at the bottom, and the solution is inside this round bottom flask. There's an ethanol water solution in there. And since ethanol has a higher vapor pressure, but a lower boiling point, then as the solution of ethanol and water heats up, as the vapor accumulates above the liquid, it's going to be more enriched in ethanol because it has a lower boiling point. So as that mixture evaporates, we have a more enriched ethanol solution, or an ethanol component in the vapor phase. And then these little guys here, these little lines, I'll zoom up on that, right? These little dashed lines on the column here, those are called plates. And what those are there for is to act as a surface for the vapor to condense. So when the vapor condenses, it is now in a composition that is the same as what the liquid was in, or so what the vapor was in right down here, right? So if it was more enriched in ethanol in the vapor phase, now it's going to be more enriched in the liquid phase as it condenses here. And then as the apparatus heats up, now this plate is going to evaporate, and then that's going to be more enriched in ethanol. It's going to condense on the next plate and be even more enriched, and so on and so forth as it goes up the distillation column. Okay, and then once it gets up to the top of the column, it reaches this condensing tube, which has a jacket of cold water flowing over it. And then what that does is it condenses the vapor, which is accumulating up at the top here. And then it is then collected in this flask here. Okay, so then you're going to get some hopefully pure ethanol in this case, or whatever the more volatile component is going to be the one that is collected in the collecting flask there. Okay, so this is a way that we can separate different volatile components just based on the vapor pressure and their difference in boiling points. So just another way to show how this works. Okay, so if we have a mixture of heptane and octane, you can see heptane has a different boiling point than octane. So heptane at 98 degrees Celsius, octane at 126 degrees Celsius. So if we start off with a 50-50 mixture of octane and heptane, what happens is when it reaches its boiling point, at whatever temperature that is, it's going to be somewhere between 126 and 98 degrees Celsius. Okay, so the blue line here represents the composition of the liquid. The red line represents the composition of the vapor. So what this is showing here on the right is a blow up of the graph on the left. Okay, so this point here, point 1, that's the 50-50 mixture where we start off with. So we can see that there's a 50-50 mixture of octane and heptane. That's represented by this vertical line here on the graph and on the blow up. And then since the heptane is more volatile than the octane, when it enters the vapor phase, the composition is actually going to be this point right there. So the composition, you can see, is headed towards 100% heptane. So this is the 100% heptane side here. This is the 100% octane side here. So as the evaporation occurs, we get more heptane in the vapor, and then as it condenses, right, this red line down here condenses with the same composition as the vapor, and then that liquid then, or that solution then evaporates and is even more enriched in heptane as it goes farther and farther up the column. Okay, so the liquid evaporates, it's more enriched in the more volatile component. It condenses on one of the plates with the composition of the vapor, which is now more composed of a higher concentration of heptane. That then evaporates as the apparatus heats up, and again the vapor above that particular plate is going to be even more enriched in heptane. It's going to condense in the next plate. The next plate's going to heat up. The vapor is going to be even more enriched, and so on and so forth. So hopefully by the end what happens is we get a separation of heptane and octane, where heptane would be the one that is collected in the flask and octane would be the one that is sort of left behind. So this slide shows what it would look like if you had a deviation from Raoult's law. So remember, Raoult's law is basically saying that we have the pressure of the solution is going to equal the mole fraction of component 1 times the pure vapor pressure of component 1 plus the mole fraction of component 2 times the vapor pressure of pure component 2, and so on and so forth. So if the intermolecular forces were very similar, then this particular equation would represent or predict what the vapor pressure would actually be. And that is shown on these dashed lines on the graph. So this here shows, I'll do it in a different color, so orange here, I'll do this, is the total vapor pressure here. And then the other dotted lines show the composition of each of the two components, component 1 and component 2, increasing or decreasing depending on which way you're looking at the graph. Okay, but you can see those are all straight lines. The dotted lines are straight lines, but the red, blue, and purple lines are curved. And they're curved in both cases because of the differences in the intermolecular forces. Okay, so if you remember back to chapter 10 in General Chemistry 1, okay, there's differences in things that are polar, that have hydrogen bonds, that are non-polar, but there's differences in the strengths of those intermolecular forces. So you would see a negative deviation, so the graph on the left, if the solute-solvent interactions, so the intermolecular forces between the solute and the solvent, are greater than the interactions between the solvent and the solvent. Okay, so that basically means that the solvent and the solute are really attracted to each other. So it's a little bit harder to separate them. So even as we're adding heat or energy to the solution, since the solute and the solvent are kind of really well attracted to each other, it's going to take more energy to release that intermolecular force and to force it into the vapor phase. Okay, so that's why we see less vapor pressure, right, from this purple line than we would expect because of those interactions. Now, the opposite effect happens if the solvent interactions are greater than the solute-solvent interactions. So in this case, the solvent really likes to stay together and it doesn't like to interact too well with the solute. So it requires less energy to separate the solute and the solvent. So what we would expect with Raoult's law would be this dashed line, but what we see is because it's a lot easier to separate the solute and the solvent, then we see a positive deviation. So it takes a little bit less energy for or to break the intermolecular forces to turn the solution into a vapor. Okay, so now we're going to talk about vapor pressure of solutions, but where one of the components of that solution is a non-volatile solvent. So the previous section was all about two volatile things. This would be about one component that's volatile and another component that is non-volatile. For example, salt water. So in this case, the water would be volatile because it can evaporate, but the salt obviously can't evaporate, right? If you just left that by itself, salt water to evaporate, the water would go away, and what you'd be left is salt in the end, right? The salt's not going anywhere. So what this is showing, or this picture is showing, that if you had on one side of a divided container pure water, and on the other side seawater. Okay, the only difference between those two sides of that container is that one has got salt in it and one doesn't. So what happens over time is that the pure water over time evaporates faster than the seawater. Okay, so what happens is we have more evaporation happening on this side of the container. Well, actually, I will say the evaporation is more on that side of the container than it is on this side of the container. Okay, but what we can also say, though, is we can look at condensation as well, because remember, when we're talking about vapor pressure, it's an equilibrium between evaporation and condensation, right? So on the left-hand side, we would have a certain rate of condensation. We'll call it 4 arrows, just like we did previously. But since what is up here, right? What is in the gas phase? The only thing that's in the gas phase is the water, right? There's no salt up there. So the condensation rate is actually going to be equal on both sides. So this is also going to have, say, 4 arrows pointing down. So the only difference between both these sides in terms of evaporation and condensation rates is that the pure water evaporates faster than the seawater does. And that has to do with intermolecular forces again. So because the seawater on the right-hand side has the salt in it, right? The salt, the negative and positive charges are kind of holding onto the water a little bit more strongly than they would if it was just water, right? So remember intermolecular forces. The water, the pure water side, right, this side over here, has hydrogen bonding, whereas the other side, the seawater side, has hydrogen bonding between the water, but it also has ions in there, right? Those ions are much stronger charges, or much larger charges than the partial charges that are present in water, right? Remember when we were talking about most of the intermolecular forces are partial charges, whereas an ion is a full +1 or a full +2 or a full -1. Okay, so those are stronger charges. Those are keeping the water in solution a little bit more strongly, right? So that's why when we leave this over time, then we have a nearly empty side of water, and then on the other side, the right side, this is just diluted seawater now, because the water from the left-hand side has moved over and condensed into the other side. Now, Raoult's law is about the same, except we only have to consider the volatile component, right? We don't have a volatile component 1 and a volatile component 2. In this case, we just have one volatile component. So we need the mole fraction of the solvent, and then the pure, or the vapor pressure of the pure solvent as well. So those will both be related to water in this particular case. Okay, so let's just go through a quick example, and I'll switch over to my whiteboard so I can show you the solution. I've already written out, but I will go through it kind of in steps here. Okay, so the one piece of information that we don't have in the question that I probably should have put there is that we will need what's called the KB I should get to the right question. Here we go. Let's try this instead. Okay, this is the right question. All right, so we got most of the world's supply of maple syrup is produced in Quebec. We're given some information about how concentrated the sugar is, right? 66% by mass. And then we're asked what the vapor pressure is in atmospheres of a 66% aqueous solution of sucrose and water, right? So sucrose is going to be the thing that is not volatile, and water is going to be the thing that is. Okay, so a couple of things we have to note here is, since we're asked for vapor pressure, we're going to be using Raoult's law, right, which is right there. So the vapor pressure of the solution is going to be given by the mole fraction of water times the pure vapor pressure of water. And it's not given in the question directly what the vapor pressure of pure water is, but we are given a temperature of 100 degrees Celsius. We should recognize that as the normal boiling point of water. So we can assume that at the normal boiling point of water, the pure vapor pressure of water is going to be 1 atmosphere. Okay, the other thing we're not given in this question is exactly how much sucrose we have in terms of a mass. Okay, so we're going to need to find what mole fraction is next. We already know this guy here, that's the 1 atmosphere, but we need to know the mole fraction of water. And to do that, we need to figure out how many moles of water there is, but we also need to know how many moles of sucrose there is because we need the moles of everything, right? That's the bottom of the fraction. We have the moles of the water going to be on top, and then the bottom is going to be the moles of water plus the moles of sugar. So since it's 66% by mass given in the question, we can just assume that, hey, we got 66 grams of sucrose and 100 grams of total solution. Okay, that just makes our life a little bit easy. Okay, so if we have 100 grams of solution, 66 grams of it are sucrose, then we must have 34 grams of water. Okay, so once we've figured this out, then we can go through the steps. And again, since we're doing mole fraction, we need to find moles of things. So the first thing we'll do is we'll find the moles of sucrose. So the moles of sucrose, we'll start off with 66 grams, and then given in the question is the molar mass of sucrose, 342 grams per mole. And then if we do that calculation, we end up with 0.193 moles of sucrose. Okay, step 1. Now step 2, we need to find the moles of water, right? So we need the moles of everything, and we also need the moles of water, all right? So to find the moles of water, again, we realize that we have 34 grams, right? And the molar mass of water is 18 grams per mole, right? Oxygen's about 16, hydrogen's about 1, and there's 2 of them, so that's about 18 grams. And then if we figure out the moles of water, we end up with 1.89 moles of water. Now to figure out mole fraction, step 3, we're going to have the moles of water divided by the moles of water plus the moles of sucrose. Okay, we do that calculation, we end up with 0.91. Now this number should always be less than 1 or 1. I mean, it's never going to be bigger than 1 because you can't have more than 100% of something. That's what 1 represents. And the 0.91 basically means 91% of this particular solution by moles is water. Okay, so now we go back to figure out what the pressure of the solution is, right? Back up to the very top, right? Here's our equation. So the pressure of the solution is going to be the mole fraction of water times the pressure of water at pure water. So then we have the 0.91, which is our mole fraction, our 1 atmosphere, and so then our pressure of that solution our vapor pressure is going to be 0.91 atmospheres. So notice again, if we had pure water, the vapor pressure would be 1 atmosphere, but since we're adding some sucrose to it, intermolecular forces are helping to keep some of that water in the liquid, in the solution phase rather than in the vapor phase. So the vapor pressure of a solution is going to be less than the vapor pressure of a pure solvent or a pure liquid. Okay, and that's what we see in this. If you get a number that's larger than the pure liquid, then you know you've done something wrong. Okay. So now we're going to talk about 2 other colligative properties. Remember, a colligative property is something that depends on the concentration of the solute particles, or basically how many solute particles there are, and not the identity. So it doesn't matter if it's calcium, magnesium, sodium, sugar, chloride, whatever, right? It just matters how many there are or what the concentration is. So we're going to talk about vapor pressure lowering and also freezing point depression. Now these little circles on the graph here are a little bit off, and they're supposed to be referring to the delta TF and the delta TB. That one's pretty good over there. So you learned about phase diagrams in chapter 10, I believe. And what you would have seen is not quite all of these lines, but you would have seen probably these ones right here. So this one going up, and then a straight line up here, and then this curvy line up there. So those are probably the ones you would have seen for water. And that's what this phase diagram is. So remember, we have solids, gases, and liquid parts, or liquid areas of the phase diagram. And what it shows us is at what pressures and temperatures each of those phases exists, right? So if we have high pressure but a low temperature, we get a solid. If we have high temperature but low pressure, we have a gas, that kind of thing. Okay, so what happens when we add a solute, like sodium chloride or potassium bromide or something, to water? What it does is it lowers the freezing point. So the normal freezing point was 0 degrees Celsius, so this particular line here, for example, but lowered to whatever this would be, depending on the concentration of the salt that is in the water. Okay, and this, you're probably familiar with it. To melt ice in the winter, you put salt on the sidewalk or the driveway or your pathway, whatever else, right? That's going to melt the snow or melt the ice because the freezing point is no longer as high as it was. It's actually lower, right? So freezing point depression. And the other is boiling point elevation. So normal boiling point of pure water is here, but the boiling point of an aqueous solution is a little bit higher. Okay, so if you add a bunch of salt to water, then the boiling point is actually going to increase a little bit. Okay. And changes to boiling and freezing point solutions depend on another concentration unit, which is called molality. So molality is given by the small m, and it is the moles of the solute. So same as molarity, so small n means moles, but instead of liters in the denominator, we now have kilograms of the solvent. So instead of liters of solvent, we have kilograms. Okay, and the reason that we use molality to determine these changes is because they do involve changing temperatures, and this particular concentration unit does not change as the temperature changes. So if you think of molarity, right, molarity equals moles per liter, and as the water or solution is heated up, that should change the volume at least a little bit. So if the volume changes a bit, then that concentration, this molar concentration, is going to change. But heating up the solution does not change the moles of the solute, and it also doesn't change the mass of the solute, or the mass of the solvent, or the mass of anything. So molality is going to be constant at changing temperatures. Now, typically molality is slightly larger than molarity, but that's nothing that really matters all that much. Okay, this particular slide just shows you how to convert between molarity and molality, how to calculate molality given different types of information. So I'm just going to leave that there. Okay, so now how do we calculate boiling point elevation and freezing point depression? The equations are quite similar. So the change in the boiling point temperature, right, not the new boiling point, not the actual boiling point, but the change in it, is related to I. We've seen I before, right? That's the Van't Hoff factor, which has got to do with how the component breaks up in water, right? Sugar, the Van't Hoff factor is 1 because it doesn't ionize in any at all, right? It just goes in as sugar. It's a solid sugar molecule. It goes into water. It's just one solid sugar molecule, whereas sodium chloride breaks up into sodium plus and chloride minus, so that's Van't Hoff factor of 2. Kb is just the boiling point elevation constant. That would have to be given to you in any of the questions to figure it out. And of course, m being molality or moles of solute per kilogram of solvent. Okay, for the freezing point depression, it's very similar. Right? The equation looks pretty much the same, except we're looking at a change in the freezing point. And the only real difference is we're looking at a Kf, or a freezing point depression constant, rather than a Kb, which is a boiling point elevation constant. Now, one other thing I want to mention with both boiling point elevation and freezing point depression is sort of inherent in the name of each of them. So I want to put a circle or a square around elevation and depression. So as I was saying before, these delta T's just mean the change in the boiling point and the change in the freezing point. But since you know boiling point is an elevation, that would mean that say you get an answer where the delta TB equals 0.5 degrees Celsius. That would mean, since it's a boiling point elevation, that the new boiling point of that solution is half a degree higher than it was if it was just a pure solution. Now the opposite would be the case for freezing point depression. If the delta TF also was 0.5 degrees Celsius, that would mean that the new freezing point is half a degree less than the regular pure freezing point, right? Because you got the word there, depression. So whenever you're trying to figure out what new boiling point is, you'd have to take the pure liquid boiling point and add to it the change in the boiling point. If it was a freezing point depression, you would take the freezing point of the pure compound and then subtract what the change in the freezing point is. Okay, a couple examples here. So boiling point of seawater. What is a boiling point of seawater in which the concentration of sea salts is equivalent to 0.560 molar sodium chloride per kilogram of seawater, and the Van't Hoff factor of sodium chloride is 1.85. All right. So here it is. So this is the one where I was saying that we have some additional information that I didn't give you in the question, but there it is. So we need to know the Kb of water being 0.52 degrees Celsius per molality. Okay, we're asked for a boiling point, well, actually what the boiling point is, so what we need to figure out is the boiling point elevation, right? So we're adding some solutes, so we need to use this equation here. I is given as 1.85. Kb, I was given at 0.52 degrees Celsius per m. And then most of these calculations, what you really have to figure out is what molality is. Okay, so again, molality is the moles of solute over kilograms of solvent. So we need to know how much water there is in terms of a mass. We need the kilograms of solvent, so we'll do that first. So to do that, we have to also figure out how much sodium chloride there is, right? Because we're going to need to know, what we do is let's go back to the question here. We know from the question that we have a kilogram of seawater, right? So and we're also given how many moles of sodium chloride there are, right? So that many moles of sodium chloride in a kilogram of seawater. So if we can figure out what the mass of sodium chloride is, all we have to do is subtract that mass from a kilogram of seawater, and that's going to give us the mass of water in our seawater. So that's going to be our first step. Find the mass of sodium chloride. Okay, we're given the moles of sodium chloride, and if we look on a periodic table, we'll see that the molar mass of sodium chloride is 58.44 grams per mole. And then if we do that calculation to figure out the mass of sodium chloride, we get 32.73 grams. Step 2, find the mass of H2O, right? The solvent, that's the bottom part of our fraction here. So we got the mass of the seawater minus the mass of sodium chloride, so 1,000 grams, right? Make sure this is in grams because our sodium chloride mass is also in grams. Kilograms, 1,000 grams. Take 1,000 grams minus 32.73 grams, we get about 967 grams of water, right? So now we have how many kilograms of solvent, or that's our mass of our solvent. Now we need to find the molality of sodium chloride, right? So that's what we need in our delta TB equation. We need the molality, right? So molality is moles of sodium chloride per kilogram of water or kilogram of solvent. So that's our equation right here. We're given the moles in the equation, 0.560 moles. We just calculated what the grams were of water, but we convert that to kilograms, so that's 0.967 kilograms. So we get a concentration in molality of 0.579 molal. And then to figure out our change in our temperature, now we're using our delta TB equation. Okay, we're trying to figure out what that delta is. Right, here's our I is 1.85, our KB 0.52 degrees Celsius per molal, and then what we calculated as the molality. Right, so there is our delta TB, so that's the change in the boiling point. But again, the question is asking, what is the boiling point of seawater? Right, so what we calculate here, this 0.56 is not the boiling point. Hopefully that's obvious, right? The boiling point of pure water is 100 degrees Celsius. So if we're doing a boiling point elevation, the boiling point has to be greater than 100 degrees Celsius. And clearly 0.56 degrees Celsius isn't. So because it's a boiling point elevation, the new boiling point is going to be the boiling point of pure water, which is 100 degrees Celsius, plus the change in the boiling point due to the addition of sodium chloride. So our new boiling point is going to be 100.56 degrees Celsius. Okay, and I think I have another question next. Yes, I do. Okay, so another boiling point elevation question. This one's just asking for the boiling point elevation. I didn't give you what the pure boiling point of the solvent is, and the solvent in this case is carbon tetrachloride. So you'd have to know what the actual boiling point of that is in order to find what a new boiling point was. So in this case, we're just trying to find what the boiling point elevation is. Okay. So again, we're going to be using our delta TB equation. We're given the KB of 2.34 degrees Celsius per molal, right? So this is carbon tetrachloride, which is different than water, so it's going to have a different boiling point elevation constant. And cinnamaldehyde is given as this particular chemical equation. And because it's got carbons, hydrogens, and oxygens in it, that's really good indication that it's a non-electrolyte, kind of like sugar. Right? It's not like a sodium chloride or a potassium, whatever, bromide or something like that, or a lithium sulfate. Okay, so it's going to be a non-electrolyte, which means I, or the Van Hoff factor, should be 1. And just like the previous question, we're going to try and figure out what molality is. So we're given some masses of our solution, some masses of the solute. But what we don't have is, well, we got to figure out what moles are, right? So remember, molality is the moles of the solute over the kilograms of solvent. So let's just try and figure out what the moles are of the solute first. So in order to do that, the first thing we need to do is figure out what the molar mass of cinnamaldehyde is. So cinnamaldehyde, C9H8O, to figure out the molar mass, right? We have 9 carbons. Carbons are about 12 grams per mole each. We have 8 hydrogens, which are about 1 gram per mole each, and 1 oxygen, which is about 16 grams per mole. So our total molar mass is about 132 grams per mole. Right, so now to figure out the moles of cinnamaldehyde, right, step 2, we know how much we have, right? We have 100 milligrams of cinnamaldehyde. Right, so first thing we do is we turn that 100 milligrams into grams with this conversion factor here, right? 1 gram is equal to 1,000 milligrams. And then use the molar mass from our previous calculation to cancel out the grams and end up with 7.5 times 10 to the minus 4 moles. So that's how many moles of cinnamaldehyde we have. And now again, we're trying to figure out molality, right? Up here, the molality. So what we have to do now is to take the moles that we just calculated and divide it by the mass of our solvent, our carbon tetrachloride, which is actually given in the question, right? It says 1 gram of cinnamaldehyde, and 1 gram is the same as 1 times 10 to the minus 3 kilograms, or 0.001 kilograms. So we do that calculation, we get 0.758 mole. Right? And then now we have all the information we need to figure out the boiling point elevation. We have our Van't Hoff factor of 1, our Kb of 2.34, and our molality of 7.58, and our final answer there of 1.77 degrees Celsius. So that would be the final answer for this question. But if I were to give you the boiling point of carbon tetrachloride, the solvent, then what you would have to do is add 1.77 degrees Celsius to that particular number to get the new boiling point. Okay, just a summary of concentration units. You might find that's useful when doing homework, studying for exams, that kind of thing. And I'm just going to leave that there. And the last couple slides here, just something about solubility of gases and Henry's law. So Henry's law relates the concentration of a sparingly soluble gas in a liquid to the partial pressure of the gas. So a sparingly soluble gas might be something like oxygen or carbon dioxide in water. Okay, so not a lot of it dissolves in there, but there is some that does dissolve, obviously, or else we wouldn't have anything living in our oceans and our lakes and our rivers. Okay, so the concentration of the gas is equal to Henry's law constant, which is Kh, times the partial pressure of that particular gas. Okay, and the solubility of gases in liquids is a little bit, I want to say, counterintuitive for how it works. So, for example, if you had sodium chloride and dissolved it in water, okay, what do you think would happen if, or to the amount of sodium chloride that you could dissolve in water if you heated it up? What you're probably thinking now is that while you heat it up, you can dissolve more sodium chloride, and that would be correct. But gases are different. Gases are actually the opposite. So if you have oxygen dissolved in water and you heat it up, what happens is more oxygen is actually released from the water. Okay, so less or a smaller amount of gas dissolves in water as it heats up. So if we want to relate this to something like, climate change or global warming, if the oceans are a major sink for carbon dioxide, which is true, right? A lot of carbon dioxide actually gets dissolved in the oceans. But as more carbon dioxide is added to the atmosphere, that should result in more carbon dioxide being dissolved, because we're actually increasing the pressure or the partial pressure of carbon dioxide in the atmosphere as we add more carbon dioxide to the atmosphere. But we know that carbon dioxide is a greenhouse gas, traps heat, and results in the atmosphere heating up, right? The atmosphere heats up. What does that do? It also heats up the oceans. So if the oceans heat up, the rivers heat up, all the water bodies heat up, all the carbon dioxide, well, not all of it, but a portion of that carbon dioxide that is dissolved in the water is actually going to be released, right? So the hotter the earth gets, the hotter the oceans gets, the less carbon dioxide they can dissolve. And that means more of that carbon dioxide that was dissolved in the oceans is going to be released into the atmosphere. So it's kind of like a cyclic effect, right? Or I can't think of the word. I'll just explain it one more time. I'll just say it again. As you heat up the atmosphere, the water heats up. More carbon dioxide gets released in the atmosphere, which heats up the atmosphere more, which heats up the water more, which results in more carbon dioxide in the atmosphere, and so on and so forth. All right, so it's I can't think of the word, but you know what I mean, right? It's basically a bad situation. All right, okay. So last slide here. This is just giving you some ideas of what Henry's law constants are, and they don't really mean too much. Those units are kind of weird, moles per liter times atmosphere, right? But what these numbers are basically saying, in terms of relative to each other, is that the lower that number is, the less of that gas as a proportion to others can dissolve in water. So if you look at, say, We got oxygen here, 1.3 times 10 to the minus 3, and nitrogen, 6.7 times 10 to the minus 4. What this basically says is everything else equal, there's more oxygen will dissolve in water than will nitrogen. Okay, and if you just look at the other table here, right, this is just showing oxygen and showing how Henry's law constant changes as the temperature increases. And what you can see is Henry's law constant decreases from 0 degrees Celsius to 50. And again, that just basically means that as the temperature increases, less oxygen can dissolve or can be dissolved in water.